guys, in this video I would like to talk about the results and possibly give you guys some intuition behind the paper, stronger generalization bounds for deep nets via compressive methods. What is generalization? The ability of a model to perform well on unseen data. So first of all, we would obviously assume that the trained data and the test data comes from the same distribution. So most of you would have come across a related concept which is overfitting. And what exactly is overfitting? You say overfitting occurs when a model which seems to perform well on the training data doesn't seem to replicate the same. So which can mean the model is too complex and doesn't really generalize well. The pursuit of trying to reduce the generalization error and trying to find models with better generalization inspires us to find better algorithms and better generalization techniques which gets us better models. Let's first take a look at the existing ways in which we can quantify the generalization error of the model. So let us first talk about the Rademacher complexity. So let G be a family of functions from a set Z to R, and sigma I to sigma M are the Rademacher variables. A Rademacher variable is basically a Bernoulli variable which can take values between +1 and -1 with a probability of 1 by 2. So Rademacher complexity is basically the expected average accuracy of the best model G from the family of functions capital G over all sigma. It gives you a measure of how G correlates with noise S. Next up is VC dimension. VC dimension is the maximum size of a set S that can be shattered. For example, VC dimension of a line is 3, a sphere it's 4. Now finally, we take a look at uniform stability. It measures how sensitive the algorithm is to the replacement of a single variable. Understanding deep learning requires rethinking generalization, train neural network using true labels, partially corrupted ones, which are basically one in which some labels are corrupted, totally random labels, and then shuffle the pixels up, and then use totally random pixels, and also generated pixels using pure Gaussian. As you can see, the results are rather surprising. So these graphs basically gives you an idea about how powerful the capacity of a neural network is. Since our randomization test suggests that many neural networks fit the training set with random labels perfectly, so we would expect the Rademacher complexity to be around 1 for the corresponding model class, which is just, as you can see, a trivial upper bound. Coming to VC dimensions, even though there exists a bound in terms of L1 norms, that bound isn't really relevant to networks. Also, uniform stability is rather pessimistic, so thus we need a weaker notionality. Let's see how regularization techniques like weight decay, which is basically L2 regularization, which are mainly inspired from classical machine learning theory. You can clearly see that even with all the regularizers turned off, the model performs pretty well. Data augmentation had some significant impact. Inception, you can see, achieves good accuracy even without regularization. If you observe the inception without Basnorm graph, we could see that Basnorm mainly helps in smoothing its loss. Our results seem to suggest that generalization error more or less and the model architecture. There is a need to develop better ways to bound generalization error of neural networks. So, the authors of stronger generalization bounds for deep nets via compression approach suggest a simple compression-based frameworks to get better bounds. So, the basic idea is that you can bound the generalization error of a complex classifier F using a simpler classifier G which has been trained on the same data and incur the same losses. So the paper suggested two compression approaches. The first one via simple low-rank approximation and the second one via random projections coupled with noise stability properties of a network. So let F be a class and GA be a class of classifiers. We say F is gamma is compressible via GA if there exists a function in G such that for element of S we have for all Y such that the given condition. So now we're going to talk about one of the first results of the paper where we bounded the generalization error of the compressed classifier G. The authors have considered a slightly different setting where the compression algorithm is allowed a helper string S, which is arbitrary but fixed before looking at the training samples. So let S be random initialization used for training the deep net. So then they've essentially compressed the difference between the final weights and S. This can apparently give better generalization bounds. The result here can easily be derived by using a famous concentration inequality called Chernoff bound. Observe that this framework proves a generalization not of F but of its compression G, like the path-based framework for deep nets. The compression framework also gives easy and short proof of the generalization bounds of the Nature et al. Here, we use a simple lemma to make A cap be a truncated version of A, where singular values that are smaller than a particular value, say delta into spectral norm of A are removed. Spectral norm of A cap minus A is less than or equal to delta into spectral norm of A, and rank of A cap is at most Frobenius norm of A squared by delta square spectral norm of A, which also makes sense intuitively. Let's now take a closer look at the generalization bound given here. The second part of this expression is something called a stable rank of the layers. Since the square of the Frobenius norm of a matrix is equal to the sum of squares of the singular values, and the spectral norm is the square of the largest singular value, the sum of stable layer is obviously a more natural measure of their parameter count. The first part, the product of the spectral norm of the weak matrices, is related to the Lipschitz constant of the network. Lipschitz constant is the maximum norm of the vector it can produce, given the input is a unit vector. That is, say you have a function f for all x and y, if norm of f of x minus f of y is less than or equal to L into norm of x minus y, then L here is your Lipschitz constant. So now let us take a look at the second method given. We first introduce some noise stability properties that imply better compression, and then we randomly project linear projections onto the lower dimensional subspace. So before going into the noise stability properties of the network, let us first define something called noise sensitivity. So this is the equation of noise sensitivity. As you can see, low sensitivity implies that the matrix has very high singular values which can carry the signal x where the noise attenuates. We get a pretty nice result for the noise sensitivity of a matrix M with respect to the Gaussian distribution. This proof is very trivial and can be easily derived using the fact that expectation of eta transpose is 0. So the above proposition suggests that if a vector x is aligned to a matrix M, the matrix becomes less sensitive to noise at M. So let us now discuss some noise stability properties that can maybe imply better compression. First up is layer cushion. So layer cushion is more or less a ratio of the norm in the data space to the actual norm in the entire space. So by norm in the data space means you're only considering the components in the directions in which the data exists. Cushion, as you can see, is related to the concept of noise sensitivity and can be thought of as a reciprocal to noise sensitivity, which is 1 by mu1 square in the case of Gaussian noise. Second property we're going to discuss is interlayer cushion. It can be more or less thought as a generalized version of the layer cushion term we've defined above, except this here is for any two layers I and J. J is the Jacobian matrix. The third property we're going to discuss here is activation contraction. It is defined as the smallest number such that for any layer I, norm of phi of x is greater than norm of x by c. As you can see, it more or less quantifies the intuitive observation that only almost half the layers of ReLU are active at a time. So for ReLU, it will be 0.5. So the final property we're going to talk about is interlayer smoothness. So let eta be the noise generated as a result of substituting weight in some of the layers before layer I. We define interlayer smoothness rho delta to be the smallest number such that with probability 1 minus delta over noise eta for any two layers I less than j, for any x, the given condition holds. So in order to make more sense of the condition given above, let us take a single layer, a simple single layer case where j is equal to I plus 1. So as you can see, after doing some basic operations, when the activation function is ready, has an opposite sign, phi dash of x of I plus eta and phi dash of x of I disagree. In practice, the noise is well distributed and be a small portion activations change from active to inactive. Hence, we can expect norm of eta to be way greater than norm of nu. So in general, we can see that for a single layer, raw delta captures the ratio of input weight alignment to the noise weight alignment. Let's move on to the second part of this compression framework, which is randomly projecting the linear projections onto a lower dimensional subspace. This is very closely related to the idea of a very famous lemma called Johnson-Lindenstrass lemma. The important thing to note here is that unlike PCA, Johnson-Lindenstrass does not assume that our data is constrained to a lower dimensional subspace. So let us walk you through the setup. Let there be n data points such that ui belongs to Rd. So we would basically like to find a function f which maps from Rd to Rm and m very less than d while preserving the interdata distance. To do that, we use a constant epsilon to bound the ratio of the interdata distances in the new lower dimensional space to the interdata distances in the original space. Using simple linear algebra concepts and sub-exponential random variables, we can show that there exists a map to generate an f which satisfies the amount demand such that m is equal to omega log n by epsilon square. So a general idea of is to first perceive the weight matrices by random projections on a linear dimensional subspace. And using the basic idea of the JLS, which we have discussed above, we can show that the output hasn't changed much. And finally, apply some noise stability properties on the result mentioned in the next slide and bound the Rademacher complexity by the Dudley entropy integral. Following lemma from the Neishaber paper based on simple induction of the noise shows how the noises from different layers adds up. Product of the norm of the weight matrices can be represented using the noise stability properties we have defined above. Beta can be approximated by C raised to D, where C is the activation contraction into norm of the output by norm of the input into products of all the rare cushions. And we finally compare the new ways approximating all parameters. Now, let's take a closer look at how the noise stability properties we've defined above help in generalization, that they do in the first place. So here we plot all the four properties, layer cushion, minimal interlayer cushion, contraction, and interlay smoothness for the initialized network and after the network is fully trained. So that interlay cushion, activation contraction, and interlay smoothness, especially interlay cushion, behaves nicely even after training. Layer cushion quantifies its noise stability has drastically improved during the training, especially for the higher layers. Also observe that the activation contraction decreases after the neural net has been trained. All these graphs suggest that layer cushion is the real driver phenomenon behind generalization. So let us now train a neural network with normal data and corrupted data and then investigate these properties. As you can see, the layer cushion has a higher value for normal data than corrupted data, and the activation contraction has a lower value for normal data than corrupted data. Basically, the trained network will obviously have a larger cushion and a lower activation. So we can clearly see that a larger cushion and a lower activation contraction help us better. So let us compare the bounds we have defined now to the already existing bounds. Like from clearly see that new bound is order of magnitudes better. Let us also take a look at the actual compression. Observe that the compression in earlier layers are very high, but it's very low in the later layers. So, a couple of final remarks before. Note that we can also use these same methods to derive generalization bounds for CNN. So, the latest work in this area uses something called stable rank normalization, which minimizes the stable rank and gets much better generalization. So, thank you guys for watching this video, and hopefully, you would have gained some new insights from it.